Product and quotient rules. So yesterday I stated the product rule and I said I'd prove it today, but actually I changed my mind. The proof is in the book. I'm going to prove the quotient rule today, which is a little harder. So I'm just going to state the product rule first. I'll state the quotient rule, and then I'm going to prove the quotient rule is true. So the product rule says if you try to take the derivative of two functions that are multiplied together, then you can write that in a couple of different ways. The derivative of the first function times the second function plus the first function times the derivative of the second function. So basically you hold one function still, take the other derivative, multiply, then switch, do it the other way around. So that's the product rule. Quotient rule is a wee bit more complicated. So if I take the derivative with respect to x of the division of two functions, then it's kind of similar to the product rule here. I'm going to take the derivative of the first function, multiply by the second function as is, the bottom function, but then I'm going to subtract the top function divided times the derivative of the bottom function. And then I got to divide by the square of the original bottom function. All right. And I'll give you some tips about how to remember this formula, but right now I'm going to prove this one. The proof of the product rule is in the book. I trust you can read through that. And after this proof, I think the proof in the book for the product rule will make a little more sense. So I'm going to justify this is true by using the limit of the difference quotient, because that's where derivatives come from. And so we're going to apply the limit of the difference quotient. So to get the derivative of anything, we have to take the limit as h goes to 0 of our difference quotient. And the difference quotient says first replace the x's with x plus h's. So that's just f of x plus h over g of x plus h. And then I want to subtract the original function, which was just f of x over g of x. Right, so we have that complicated function there, and then divide all of that by h. Now, if we try to plug in h equals 0 right away, we'll get 0 over 0, and we can't do anything, so we got to do a bit of algebra on this. So what I'm going to do first is I'm just going to focus on the numerator. And remember that four-step process I told you before for applying this limit of the difference quotient? The first thing we do is we figure out what f of x plus h is. Well, in this case, it's f of x plus h over g of x plus h, and there's nothing I can do to that. So the next thing I have to do is the difference. So I'm jumping to step 2, because step 1, there's nothing to do but write it down. To subtract two functions, two fractions, we need a common denominator, and the common denominator just has to be the product of those. So the new denominator is going to be g of x plus h times g of x, and then we're going to have to multiply that g of x up there, and the g of x plus h gets multiplied up there. So I'm just going to skip the limit for a little bit while I do a little algebra. The numerator now is f of x plus h times g of x, right? So that's this right there, and then minus g of x plus h times f of x, and all of that is over common denominator g of x plus h times g of x. All right, so next I just have to apply some algebraic wizardry here, and the trick is we're just going to insert a little bit in between here. So I'm just going to expand this, give myself a little space to work. And then over here, I've got my minus g of x plus h times f of x. And I need to factor this out, but I'm going to throw a couple of terms in the middle and then use the factor by grouping technique you learned way back in an Algebra 1 class. So in the middle here, I'm going to stick an f of x plus h times g of x plus h. Now, I can't just throw something in there without changing it. So since I'm subtracting it here, I'm going to add it right next to it. So this thing I threw in the middle, right, I'm just subtracting and adding the same term. So essentially I'm just putting 0 in the middle. However, this gives me some interesting stuff to work with. Now I still have this denominator hanging out there, so I got to draw that back in. So that is all over g of x plus h times g of x. Now, throwing this term in, what that gives me is in the first pair here, so let's isolate this first part, I now have a common factor of f of x plus h. So from that first pair, I'm going to pull out an f of x plus h, and that leaves me a g of x minus g of x plus h. In the other pair of terms, you'll notice there's a common factor of g of x plus h, so I'm going to pull that out. So I've got this plus right there. I'm pulling out g of x plus h, and that leaves behind f of x plus h minus f of x. And all of that is over g of x plus h times g of x. Oops. All right, so what's the point of all this right here? Well, what you should notice now is that this f of x plus h minus f of x, that's the numerator of the difference quotient for the derivative of f. This one right here, though, is backwards. Instead, this one says g of x minus g of x plus h. I would rather have it say g of x plus h minus g of x. So if I change the order of the subtraction, that changes the sign of the result. So rewriting that part, essentially what I'm going to do is from that first piece, I'm going to factor out a -1 in front of the f of x plus h. And then this now right here becomes g of x plus h minus g of x, which is the numerator of the difference quotient for the derivative of g. And then over here, I had g of x plus h times f of x plus h minus f of x. All of that right there is still divided by g of x plus h times g of x. All right, so I've done a whole bunch of algebraic wizardry here on just this numerator, and there's really not too much more I can do there. I'm ready to now divide by h. So I'm going to bring in that divide by h. And remember, when you divide by fractions, taking something and dividing is the same thing as taking that object and multiplying by 1 over h. Right? Dividing by a number is multiplying by the reciprocal, so that's what I'm going to do here. I'm going to multiply, oops, I'm missing a parenthesis here. I'm going to multiply all of this by 1 over h. Okay, so multiplying by 1 over h basically means h is now part of this denominator, and everything in the numerator is also divided by h. So what I can do next is rewrite it this way. Let's see, we've got negative f of x plus h times g of x plus h minus g of x, oh, and freak out, plus g of x plus h, parentheses are super important here in the right spots. And I'm going to break the division up into 2 parts. So I'm going to cut that there, and I'm going to cut that there. And then I've got my denominator is now g of x plus h times g of x. And we also have an h as part of the denominator from here. Same thing over here. G of x plus h, g of x. And then we have an h down here. And what I want to point your attention to here, now that I've split on this addition right there, is that this chunk right here should look familiar. And this chunk right here should look familiar. going to throw in the limit as h goes to 0 now. All right, so this highlighted piece, that's the difference quotient for g of x. And if I take the limit as h goes to 0 of that highlighted piece, that right there is g prime of x. Over here, this right here, f of x plus h minus f of x over h. Oops, I accidentally highlighted that g of x there. Let me see, can I fix that? I pull the highlight out and try it again. I meant to just highlight, oops, that's not a highlighter. This part here. That right there is the difference quotient for f of x. And if I take the limit as h goes to 0, that right there becomes f prime of x. So I'm just going to scribble over this a little bit. I do have an, oops, wrong color. Don't forget, we do have a negative sitting out there we have to contend with. But we're going to let h goes to 0. And as h goes to 0 here, right, this part becomes just negative f of x. This part right here, as h goes to 0, that's g prime of x. So yes, so Cole, I have the same thing in algebra. If I can cancel shit, I'm like, yeah, let's cancel it. So I think Cole's referring to the overwhelming urge to cancel those guys, but don't do it. Don't. Hang on just a second, I'll show why. It has to do with having a common denominator. Okay, so I'm not going to do that right now, even though I'm dying to cross it out. I'm going to resist that urge. Okay, so just bear with me a sec. So now I'm here at my plus. As h goes to 0 here, that's just g of x. This part here is the derivative of f of x. So that's f prime of x. Now I still have the denominator. The h's down here disappeared with the derivative. Okay, they turned into the derivative there, so they're gone. So all that's left is the g of x plus h times g of x in both spots. And remember, h is going to 0 there, so that becomes g of x times g of x. Now that happens here and here, so that is my common denominator right there. So that's why I couldn't cancel. I need a common denominator to put these back together. So my common denominator is g of x times g of x. So whipping this around just a little bit, let's switch colors. That's not the right color. Green for success. Red isn't failure. I don't know why I said that. G of x times g of x is the square of the function g of x, which we usually write like that. And then I'm going to switch the order of these to put the minus in the middle. So I'm going to take the g of x times f prime of x. I'm going to write it as f prime of x times g of x, and then I have minus f of x times g prime of x. And that is the quotient function, the quotient derivative that I stated up front, but the proof of it. So I don't expect you to reproduce this proof, but I just wanted to show you it does come from somewhere. And the bottom line is every derivative in existence ultimately has to come from the limit of the difference quotient. Okay, so without the limit of the difference quotient, we don't have derivatives. All we're doing now in section 3 is developing these shortcut rules, these patterns that allow us to not have to do that all the time by saying, hey, I recognize this. I don't have to do the limit because I know what the result looks like. Well, if I want to take the derivative of the division of two functions, this is what the result is always going to look like. All right. So some tips for remembering the order of stuff. So back here, it is very much like the product rule, right? Notice here I have, in the product rule, I have f prime times g plus f times g prime. And over here in the quotient, I have f prime times g, but instead there's a minus f times g prime, okay? So the way I remember the minus there is just from a rule from algebra. So think back to algebra for a minute, and 1 over x is the same thing as x to the power -1. And then we have that power rule that says when you take the derivative of something to a power, you bring that power in front and then reduce the power by 1. So -1 minus 1 would be a -2. So I didn't prove that you could use the power rule with negative negative powers, but it turns out you can. So the derivative with respect to x, and I'll prove this another day, of x to the -1, which is 1 over x, is negative x to the -2. And so if you look over here, there's parts of that here. Highlighter. So here's that negative that goes with the bottom function, right? And that's this negative here from the -1 power. And then the square here is down here. And just remember rules of algebra, a negative exponent means you could change the exponent to positive by putting it in the opposite position. Numerator jumps to denominator, there'd be a -1 up here, right? So here's that -1 there, here's that power of 2. So the way I get the quotient rule right is just by reminding myself the subtraction, the negative, always has to go with the derivative of the denominator. And that helps me keep the order correct. Ooh, man, that was a workout. Okay, let's apply it. So I'm going to make up a problem to do. New page. All right, we're just going to apply it on a relatively simple example. Let's take the derivative with respect to x of 2x squared plus 3x plus 1 divided by x squared. And often, because we have so many rules, there's more than one way to come up with a derivative. I'm just going to apply the straight quotient rule. So this polynomial in the top, that's my f of x. And this x squared in the bottom, that's going to be my g of x. Okay. So I need to know what is f prime of x, which sometimes I write out ahead of time. So that would be 2 times 2 is 4x plus 3. And the derivative of the bottom, g of x, is just simply 2x. And so the quotient rule says take the derivative of the top function first. That is 4x plus 3, parentheses are important. And just multiply by the bottom function untouched. Then subtract, leave the top function alone, 2x squared plus 3x plus 1, multiply by the derivative of the bottom function, which is 2x. And depending on the function, you might need parentheses around both. So you might sometimes need to do that, depending on the two functions. All divided by the bottom function squared. And I recommend starting out this way and then cleaning it up. All right, so cleaning this up, we have to distribute. So that's going to give me 4x cubed, right, plus 3x squared. And here, I'm going to distribute the minus and the 2x together. So I'm going to be careful with your signs. Sometimes we want to do this in 2 steps. So it's going to be a minus 2x times x squared, which is what, 4x cubed. And then minus again, negative times a positive, 2 times 3 is 6x squared. And then minus again, 2x. So that's my numerator. My denominator is x to the 4th power. And often these reduce quite a bit. So let's see, what do we got? 4x cubed minus 4x cubed. Hey, that's sweet. Those guys are a 0. And then otherwise we have some like terms. So I have a 3x squared minus 6x squared is negative 3x squared. So those guys are done, and then minus 2x. And so usually I like to mark off that I've dealt with everything so I don't lose track of stuff. So find ways to account for what you've done so you don't miss things. All that's divided by x to the 4th. And I can pull an x out of the numerator, so I can factor an x out. Negative 3x minus 2 is left behind. I guess I could have factored a negative 2, but that's all right. Did I do that right? Looks like it. All divided by x to the 4th power. And so x goes into x to the 4th, leaving an x cubed in the bottom. And in the top, I have negative 3x minus 2. Now, how do I do that? How do I check it? Well, there's only a couple ways to check this. One is just review your work, make sure you didn't make any algebraic errors. 2 is to pick a number for x and see if you found the right slope at the point on that curve. So we could certainly do a graphical check on that. But I could try to do this a different way. And I'm going to cheat a little bit and do this a different way, just to see if I get a similar answer. So new page. I'm going to take the derivative with respect to x of 2x squared plus 3x plus 1 over x squared. Let me make sure I copied that right. Looks right. And I'll show you what I mean by cheating in just a second, because I'm going to apply a rule I haven't exactly proved yet. I'm just going to divide everything by the x squared there. So I'm going to say, what's 2x squared over x squared? And what's 3x over x squared? And what is 1 over x squared? And doing that gives me a different form of this function. X squared divided by x squared is 1, so that's just a 2. Then I have plus. And if you just think about this by applying the rule, you know, x to the n over x to the m equals x to the n minus m, then x to the first over x to the second is x to the 1 minus 2, which is x to the negative 1. So I'm going to rewrite this as 3 times x to the negative 1. And here, 1 over x squared could be written as x to the negative 2. And the reason I'm doing that is I'm going to apply the power rule. Now, my proof of the power rule yesterday only applied to whole numbers, but it turns out the power rule applies to other numbers that are fractional or negative. And I'll prove that in a couple of days, but I'm just going to cheat and use it anyway. So applying the power rule here, derivative of 2 is 0. And then the power rule for this part right here is bring the power down. So that would give me negative 1 times 3, which is negative 3. And then I have to reduce that by 1. Negative 1 minus 1 is going to give me x to the negative 2. Next, I have plus, bring the power down, so that's going to give me a negative 2, and then reduce that by 1. That's what the power rule says, drop it by 1. Negative 2 minus 1, so that's going to give me minus 2 x to the power negative 3. So this is another version of the derivative. Now it looks different than what's on the other page, right? But I'm going to show they're the same here by just doing that same algebra I did earlier. I can view this as negative 3x over x cubed minus 2 over x cubed. And if we rewrite that with negative exponents, we're going to get negative 3 x to the negative 2, right? Because there'll be a leftover x squared in the bottom. X squared in the denominator is the same as x to the negative 2 in the top. And here, this is simply just 2x to the negative 3. And so if I rewrite this with negative exponents, I get exactly what I have here. So what's the point of that? Well, anytime you do a complicated problem, there is more than one way to skin that cat. So it turns out in this particular problem, if I use the product rule and some fancy algebra here, I could do it another way. If I'm not allowed to use the power rule on negative numbers, then this is the only way to do that. And there are certainly going to be some problems we come across where there is no choice but to use the quotient rule. It's the only option we have. Okay, so the trick here is you just getting used to applying these two new rules here, the product rule and the quotient rule, and that's what the whole second part of homework is all about. And we are almost out of time. We have 1 more minute. So let's see, Cole had asked an extra question. So if anyone wants to hang out and look at that question, I'm going to answer that next. Otherwise, have a good day. Remember, if you are stuck on math, there's always a message your instructor button by each question. You can message me and I'll get back to you. And I have office hours Monday through Friday at 10 o'clock. There's a link to it in the syllabus. All right, have a great day, y'all. Cole, you going to hang out and do that problem with me?